n'a pas d'announcement particulier pour nous? All right, welcome everyone to today's session. We're going to start today by a talk by Emmanuel Abbe from Princeton University, who's going to talk about graph powering.
Thank you, Philippe. Thank you to the organizer for inviting me. A pleasure to be here. So today I'll talk about something that was a joint work with two students at Princeton. Well, Colin is no longer a student. He just graduated from the math department. He's going to be here in about a month or two. He's phenomenal. If you're around, talk to him. And Enric is still an undergrad student at Princeton Math, applying now to grad school. All right, so my original motivation was understanding adversarial robust AI. But I actually realized that this requires rethinking the stochastic block models. So I'll actually get back to the stochastic block model. Okay. So here is the...
You know this is recorded, right?
Okay. Thank you.
This is live streamed.
Okay, so that's the actual framework and the motivations. So this is a context which is, I guess, fairly common in unsupervised learning. So you have a data set, and you try to understand if there's any structure in the data set, or you want a representation of the data points that's useful. So it's often easier to measure interactions among data points, like pairwise, for example. Or sometimes it's just given to you, like it could be friendship in a social network. It could be that you count the co-occurrences of words in a corpus of words, of documents within a distance. If you do image segmentation, you will look at the similarity between pixels inside an image. That's PPI networks, protein-to-protein interactions. You see if two proteins are in contact or not. Once you have this matrix of interaction, what you often do, well, I view it as a graph or as a weighted graph. And then often what you want to do is come up with a compression of that weighted graph. By compression, very often what's commonly used is just a spectral methods. Some sort of just look at some dominant eigenvalues or all the non-negligible eigenvalues. And hopefully this gives you a useful representation of the data points, a lower dimensional representation. Okay, what's interesting is you start from something that is very abstract, that has nothing Euclidean, and you end up with an Euclidean embedding. So here are two examples. This is the most relevant one for this talk, spectral clustering. So we have an undirected graph. This is the matrix that we build, the operator, the graph Laplacian. D is diagonal matrix with the degrees of the nodes, and A is the adjacency matrix of the graph. So the motivation is that quadratic form with the Laplacian exactly measure the variations of your vector x on the edges of the graph. Think of an unweighted graph for now, simplify. Okay, so now in clustering, what you would do is you would take your top k eigenvectors. This may not, you may leave out eigenvalues that are significant for this. You just want to find clusters. And that gives you your spectral embedding. So you started with a graph, an abstract object, and now you have each point in, let's say, the plane if you take the top two eigenvectors. Top can mean different things. In this context, it's the lowest eigenvalues. Sometimes it will be the largest, but it's always clear usually from the context which side you want to go. All right, so then once you are in this Euclidean setting, you can run an algorithm like k-means or greedy algorithm to actually find the clusters. The point is that it's much easier to solve the problem in this context than in the original context. All right, so that's the sparse cut motivation. Now the other example that I like to think about and use as motivation is the vector space models for word embeddings. So you are given a corpus of words, let's say Wikipedia, and you have a distance of 5. So you look at a chunk of phrases of length 5, and you count how many times, that's a co-occurrence matrix, two words are co-occurring in a small window of 5. Okay, you do a few other things that I'll discuss shortly, but the general idea is the following. Then you take the top k eigenvectors. This time you take you only leave out negligible eigenvalues, because here the motivation is not to find clusters, is to actually find vectors such that the inner product of your vectors is roughly the matrix entry. And for that you need to take all the Frobenius norm. All right, so this is like how this could look in a cartoon representation. And this surprisingly preserves a lot of semantic properties. This is a cute fact that is often mentioned. If you take the vector you obtain for the word king, you subtract the vector for the word queen, you obtain roughly the same vector as man minus woman. So that's the general motivation. You have some interactions, you build a matrix, you use some spectral decomposition, and you obtain useful representation. Except none of these really work as I described them. So let's see an example. If you generate a random graph like this, two groups of size n by 2, n is 10,000, and you put edges independently with probability a by n, where a is 2 by 2, inside each clusters, and you put edges with a lesser probability, b by n, across the clusters. This is 0.06. Then if you just apply the algorithm that I described before, the vanilla Laplacian spectral algorithm, this is the cluster you obtain. There will be your first cluster, and the second cluster will be these outliers. And this has a very thin cut. There's only a single edge. There's enough guys to make this to normalize it not too much. And this is thinner than the cut in the middle that you want to catch. Okay? So there's a lot of variants to prevent this kind of scenarios to happen. First, you can do preprocessing steps that are often used. You remove things or add things. Then you can use a normalized Laplacian, where you normalize by degrees. Random walk Laplacian, SDPs. In word embeddings, it's even more of a complex procedure. First, what you want to do is normalize the count by the individual counts of the words. And then you take some like magic kernel. It could be a logarithm. It could be a root of the value. This is what's called the PMI. Right, so this is a bit of an art. You can use neural nets. And what's important, even like PCA, which is even more basic, if you don't properly scale and center things, you will not even, most of the time, not obtain the very useful representation. So the motivation in this talk is how do we design these reliable operators? And for that, we need to understand how do we measure reliability. So we'll need models to establish rigorous benchmarks. And then the goal is to come up with a principled way to build reliable operators. So this is, I should mention here, this is all work in progress. I pressure myself to present this here and hoping we would finish the paper. We're not there, pretty far from it, so take it as everything is under construction. So okay, so we first need the models, and here are the block models. So now it's not just the usual stochastic block models. There's going to be a more general family of block models. But I will only talk about two clusters in this talk to simplify things. So we always have two random variables, x and g. X is going to be the clusters. So it's basically a vector of dimension n, which is just labeled 1 for community 1 or cluster 1 and 2. So n nodes with only binary labels. And this will be uniformly drawn at random. Or equivalently, you can think of they are IID colored. Each node is IID colored with 1 or 2. Okay, now you have a random graph on these colored vertices that is drawn conditionally on these colors, and this takes different forms depending on the model. So the first model is the one I already described before, the stochastic block model, and this depends on just two parameters, a and b, besides the number of nodes. And as I said, you just put edges independently, so that's an Erdős-Rényi graph with probability a inside each group, and then you do a bipartite Erdős-Rényi across the two groups with probability b. Yes?
Just to clarify, in the previous slide, when you said reliable operators, you want to build a Laplacian in some other way, not?
Yeah, we don't know what it's going to be like. It could be a Laplacian, it could be a normalized Laplacian, it could be other thing. The question is, we have a graph, and we want to build an operator such that the embedding is going to give us the cluster. So now this is maybe something which has been less talked about in the past years, at least in the scope of stochastic block models. It's essentially a Gaussian mixture epsilon neighborhood graph. So what is it? You just have two Gaussians isotropic in the plane. We could do higher dimension, but again, let's just talk about the plane here. The separation between the two mean is S. That's the first parameter in the that's called geometric block model. S, and then you have this distance t, the threshold. Any points that is below Euclidean distance below t, you put an edge. Okay. So these two models, they capture very different things. That's something that people like because it captures the property that is also very common in real networks, which is the small world phenomena. That is, this has a low diameter, and I could be friends with Philip. Philippe could be friend with someone from high school or friends, and I'm not necessarily friend with that person. So it is true that in many cases, there's not a transitivity in real graphs. But the problem with this is that it overshoots in that direction. It forgets that, in fact, in many cases, there is also transitivity. If Philippe knows another person here, it's likely that I also know it. So often you have both kinds of nature. This is going to the other extreme. Now, everybody here has the transitivity property. If two nodes are close and close to a third one, it's very likely to be connected. So these are two things that are very different. And we would like to actually be robust to these stochastic type of edges, like low diameter and lots of independence, and these last very geometric transitive edges. And you can imagine what comes next. We define the hybrid block model. That's going to be a mixture of these two models. So there's different ways to do the mixture. One way is, for example, you, for any pair of nodes, you flip a coin with probability h between 0 and 1. And depending on the outcome, you pick an edge from this model or this model. So now you have low diameter, but tons of triangles. And we would like to have something, operators that do not overfit to these models. This is true like locally, so you can do lots of nice things. This has lots of geometry, but we don't want to overfit. All right, so here are the figure of merits. So first we talk about the agreement of a reconstruction. So it's a number between 0 and 1, alpha. So you have a block model, you have the x and the g. You only observe the graph g. You try to reconstruct x, so you have an x-hat estimator of x. And you see that these two have an agreement of alpha if the number of nodes that have the same color divided by the total number of nodes n is alpha or more with high probability. So everything is going to be with high probability when n goes to infinity. So what is the agreement? Well, you just count how many times you got the correct color. But of course, if it's in the block model, if you put everybody instead of blue and red, you flip the colors, but you get the perfect partition. This should count as a perfect reconstruction. So we want to break that symmetry. So you also maximize over. SK is just the permutation. K is 2 here. That's the number of clusters usually. But here is just you allow to relabel the communities and make sure that you count up to recoloring. You want to count the agreement that you have. So agreement of 1 is everybody is correct. Agreement of half when you have two clusters is the lowest you can get. So we assume knowledge of the parameters. Actually, in everything I think everything I'll tell you, you can estimate this ahead of time, the estimation problem. So let's just assume that we resolve that. We have the parameters of the models. Then we have two commonly studied problems. Exact recovery is when you want to get everybody correctly labeled, the full reconstruction. And then we have weak recovery or detection when you only want to get, again, half is what you can get even with a random guess when you don't look at the graph. If I just flip a coin for every node, I get by the law of large number 50% right. So I want to beat that by a constant epsilon. Okay. So this is the least demanding recovery requirement, just beating a random guess. That's the most demanding. And then when you're in between those two, what we'll care about is to maximize the expected agreement. The fraction of nodes in expectation you correctly label. We don't know what it is, could be 80% or less. This talk is about these two quantities. That's the motivation. So let's start. So now it's going to be a bit of a story. It's unfortunately the new results come at the end, which is always risky. Hopefully we'll get there. But I wanted to really tell you how we build these things out of this story. So in the SBM, let's recall what are the interesting regimes. If I put B0, so I never put edges across the clusters, then if you want to fully recover the clusters labels, then all you need is the graph to be connected, the two clusters to be connected. Because if you have an isolated nodes, you don't know what to do with it, that already gives you a probability of error of half. So you cannot succeed with high probability. So due to Erdős-Rényi seminal papers, we know that connectivity in a graph of n by 2, in an Erdős-Rényi graph of n by 2, happens in the logarithmic degree regime. So probability of the edge is log n by n, with a constant that has to be more than 2. It's 2 and not 1 because we have n by 2 nodes. Right, so if we want to solve exact recovery in this model, when we have a b which is positive, we at least need something which is logarithmic degree. And the question is, can we even do it then or not? That has been solved. I'll recall the results. Now, for weak recovery, it takes a few minutes to realize that if you don't have a giant component, which is a component of linear size in n, then also there's no hope to do anything. So if your graph was a bunch of small components of size log n, then it's essentially the same as taking a random guess. You don't have enough connections to reconstruct. And this happens when you can go in a sparser regime where you are constant by n. Now you can remove the log n, and the constant again, there's a phase transition, has to be more than 2. So these are the two regimes, constant degree for weak recovery and logarithmic degree for exact, and the two-phase transition in the special case of B0. And now we want to deal with this case where B is not 0. So how do we get started on this problem? You see a graph from the stochastic block model. You want to reconstruct the clusters. What do you do? Well, a pretty natural starting point is to say, why don't we look for the most likely clusters given the graph that we observed, the maximum a posteriori estimator. So if you take x that are balanced, they must be balanced because there are two clusters, then the probability of observing a given clustering, a clustering x given that the graph is G, is going to be proportional to the size of the cut. So I could write it, this takes only 3 lines, but if you think about it, it's very intuitive. I'm assuming here that A is more than B, so you connect with higher chance inside the groups than across. If I give you a graph, given that the edge probability is higher inside and across the groups, if you come up with a partition which has the least number of crossing edges, you must be the most likely. Because the total number of edges is fixed, so you may as well put less edges in the cut. And this is how it scales. This is a number below 1, so you want to minimize the cut. So this is maximum a posteriori decoding is exactly equivalent to the min-bisection problem. Well, I kind of play with the law of large number here, but this is not important, whether you're exactly balanced or not. So this quadratic form is what? If your x size now, I put them plus minus 1, minus 1 in the first group, plus 1 in the second group. This object here is going to be what? It's going to be aij, xi, xj is going to be, well, if they are in the same group and there's an edge, that counts as a plus 1. If they are in different groups and there's an edge, that counts as a minus 1. So that's the number of edges inside the group minus the number of edges across the groups. Maximizing that minimizes the number of edges across the group. Total number of edges fixed is observed by the graph. So this is exactly min-bisection. That's the balancedness. And remember that this is maximizing this global probability that all your nodes are correctly labeled. So this is optimal for exact recovery because this minimizes the probability that you fail in the entire reconstruction. So if this fails, nothing else can work. But this is not necessarily the right thing to do for a weak recovery or for a partial recovery, right? That's a classical one-on-one statistics. If you want to get the optimal fraction, the Bayesian optimal estimator is not the same as the maximum a posteriori. But if you care about exact recovery and you want to ask when this succeeds or not, we answered this a couple of years ago. You need the A and the B to scale as expected with log n by n, and the two constant in front, so now B is not necessarily 0, have to be larger. The gap between their root has to be larger than root 2. And this is a phase transition again. So that's the exact recovery threshold. But this is the case where you need logarithmic degrees. Now, you can still use that, and that has been done, I think, in a vast portion of work. You can still use min-bisection, meaning maximum a posteriori, as your target for the partial case. You can say, okay, what do I do when even if I cannot solve exact recovery, why don't I still use this figure of merit in the sparse case? Maybe it gives me something which is not too bad. So now, the spectral relaxation, the basic one would be as follows. I simply relax the integral constraint on the x's and make it norm 1. So now this is an Euclidean problem. You also are, luckily, if you look at A and you plug the all 1 vector to A, you catch the degree of every node. And because of the Erdős-Rényi nature, this is fairly well concentrated. So you have an eigenvector which is close to that. So being orthogonal to that is basically telling you take the second eigenvector of the second largest eigenvalue. That's what you would do with the vanilla spectral method on the block model. Take the adjacency matrix, take the second eigenvector. Now, how would this behave? So if you write the expected adjacency matrix, and I'm going to just put my labels to be the first chunk is community 1, the second chunk is community 2. So everybody here in expectation has an A by n, that's the probability of putting an edge. Here it's all B by n, and that's the expected matrix M. So the spectrum of M is very simple. The top eigenvalue is a plus b by 2, corresponds to the all 1 eigenvector. The second eigenvalue is a minus b by 2, and that's when you put a 1 on these guys and a minus 1 on these guys. Okay, you catch this eigenvector, this eigenvalue. And then you have 0 with multiplicity n minus 2, because that's a rank 2 matrix. Okay, so now if you're very optimistic, you would think, okay, that's the expected matrix. Maybe there's some nice concentration behind it. Maybe the true adjacency matrix is not too far from it. And perhaps the spectrum of A is going to break this eigenvalue into multiple ones, but it's going to keep these two, or something that is close to these two for the top 2 eigenvalues. So that is something that takes place, but you need to have at least logarithmic degrees. In fact, this has been studied a lot. You need these papers, I think they all have something that is of the order log to the power 6n, so polylogs. Then the paper of Van Vu was really going down to constant times log, and Yun Protier too. Except that they were not exactly studying this partial recovery. They were in fact studying when you can recover most of these community labels. Now I'll just mention, that's a parenthesis, that if you care about this problem of recovering everybody, then in fact this easy program works all the way down to the threshold. So that's something we just did a few months ago, and it took a bit of time to understand. So the vanilla spectral methods take the second hand vector, not only works in constant times log n, but works all the way down to the threshold that was mentioned in the previous slides. And this was surprising, because if you are really close to the threshold, you know that the error between the true eigenvector and the expected one can be pretty large. So if the expected eigenvector will have 1 over root n and minus 1 over root n are the two possible values that it takes. The expected eigenvector is this guy. I normalized it to be unit norm. And what happens is that when you're close to the threshold, your true eigenvalues can be actually pretty large. So the norm between UK, the case component of the true eigenvector, and that's just the component. That's we're looking at the second eigenvector. This is the expected one. This can be pretty large. It can be much bigger than 1 over root n. So you would think, okay, if I round this guy, it's not clear where I'm going to end up. And what this shows is that luckily, when the values are large, they are on the right side. So you don't deviate too much on the bad side, but you can deviate on the right side. So you can actually get down to the threshold with this vanilla approach. But remember that that's not what that we're after in this talk. We are after the sparse case, when you cannot get everybody and you have constant degree. And unfortunately, this is how the spectrum looks like in the sparse case for this matrix A. The eigenvalues that you care about, the second one is hiding in a bunch of outliers. And what is the largest value you can get here? It's of this order. And how do you see that? So these are the eigenvalues that the high degree nodes produce now. So because in the constant degree regime you have lots of fluctuations in the degrees, if you apply a squared to an indicator function, that's I put 1 on a vertex v, the indicator function on vector on vertex v. This is the same as the L2 norm of AEV. When you apply indicator unit vector to adjacency matrix of a graph, you pick the neighbors of the vertex. So the L2 norm is exactly the degree of that vertex. Now the degree in the sparse case are roughly Poisson of constant expectation. You're looking at the maximal value of n Poisson. They're weakly correlated. These behave like it's at least log n by log n. So that means that that tells you that the second eigenvalue square is this. So this is going to be root of that. So it's very large, and it completely blurs the guy that you care about. Here is what it looks like. So this was Henrik had to work hard. That's a real plot. He took the block model. He ran this vanilla spectral on A. And now you see that what you catch is this is a first cluster. It's a high degree node. And this is the second cluster. Okay, so yeah?
If you prune the dangling trees, then the spectral method is expected to work, no?
If you prune, that's what I'm going to mention quickly next. That's a natural thing to try. It's not going to achieve the threshold for when you can. You have to prune so much that you actually lose your graph becomes completely broken apart. And if you prove partially, you don't get down to the threshold. Right, so this is also, notice, this is a different issue than the first one. The first issue with the Laplacian is you cut outliers, tails. Here we cut the other extreme, high degree nodes. Okay, so as a classical trick used is you trim, that's trimming, removing high degree nodes. That's something again used in many cases. They do this also in the word appendix, in matrix completion. You would also trim the largest values. But this can remove potentially useful information. And it's also not something that seems necessarily like the most natural approach. Another approach which is common is normalize the adjacency matrix. Or there's different ways that are equivalent to write it. You can do it on the Laplacian or directly on A, or you can just put the inverse on one side. All these have the same spectral behavior. Essentially, you just try to smash down the nodes by their degree so you don't are too sensitive to this type of fluctuations. But remember that if you do that, then you're back, when you normalize by degrees, you're back to the Laplacian picture or something similar. Now, you don't normalize your cut by the number of vertices, but you normalize by the volume of the degrees of the vertices, but still the same issue persists. So again, that's the same graph as before, exactly the same. If you don't use A, but you use a normalized Laplacian, then the high degree node is fine now, it's smashed down, doesn't catch energy, but you cut again another tail. Right? So that's the issue. So trimming doesn't quite work, normalizing by degree doesn't quite work. In fact, even if you use the actual true min-bisection, we believe that this will not solve weak recovery in the most optimal regime. So that we can prove that min-bisection doesn't always succeed, but it's a bit of a hack. If you take the entire stochastic block model, you put yourself close to the threshold. I didn't tell you what the threshold is, but if you are in a very sparse regime close to the threshold, then you have a lot of isolated vertices to an extent that you can have enough of them that you can create a bisection and a zero cut. So min-bisection catches these isolated vertices in some regimes when you can still solve the problem. That's a bit of a hack because you can say, okay, why don't we just look at the giant component? Yet it does capture a bit what's happening. Even if you look at the giant component, we believe that this is the picture, but we can prove it, that you have your giant. And you can actually peel out all these tails. And if you're close to the threshold for weak recovery, we believe that there's enough tails that, in fact, your cut will be, your min-bisection will be at the periphery, rather than in the clusters. But that we couldn't prove because the two are of the same order. You have to look at the constant. We didn't try too hard. I don't know if is Sen here. Did you try? Do you know? Can you prove that? I know that there was an heuristics that that min-bisection may not work, but is there a proof that it actually fails close to the KS threshold?
I think what will be true is that
in the giant only, because we can prove it if you're not in the giant. But
in the giant only.
yeah.
I mean, they will be of the same order, but yeah, the constants I don't know.
Right. So I mean, look, these papers give a very nice detailed picture about the SDP. SDP gives a even lesser cut than the min-bisection. So if min-bisection fails, because it catches such a thin cut, SDP will also fail. I believe it will. It's a conjecture, but we're not sure. All right. So now, finally, we move to the next chapter, which is we've been thinking of maximum likelihood the whole time, but remember that this is maybe not the right target. And this is an example why. So what should we do? Well, if you want to get the right fraction of nodes, then we should look at what's optimal for it, which is maximizing the number of nodes that we correctly label, the Bayes estimator. And this is what it does. So again, I'll maybe just remind you. So if you have you want to maximize the sum of, you get a 1. So I'm assuming that there's always something a little bit annoying to discuss because of the symmetry. You first have to break the symmetry because you remember there was a pi, there was this relabeling of the communities. Let's put this under the rug. Let's assume that maybe I give you a slight perturbation of the block model with asymmetric size so that we can always determine the communities labels. We don't have that symmetry. Although it's a bit technical and it's not interesting to discuss how to break the symmetry. We broke the symmetry. So now if you want to take the expectation of that, and you want to maximize this, then you try to maximize this probability. So you have to maximize this for every I. You can condition by G. You still want to maximize this for every I. So now what you want to do is pick your guy. Your x out of I is find the value of this marginal and put the most likely value, and that is base optimal. That's what we want to do. So now this is a classical example, which I think is very informative, between the difference between ML and Bayes. Let's say that this was your Bock model, something you will never see. It's a simpler case, like just this tree. So you put edges with probability A by n inside the group and B by n across. This tells you that if you look at an edge, and there is an edge here, then the confidence you have that they are in the same group is A times A plus B, those two nodes. And you think that they are in a different group with A by A plus B, by a Bayes rule, right? Because you're more likely with A than B to be in the same group or not. So that gives you, I picked this number so that we obtain the conclusion we want. So that gives you, when you see an edge, you think with probably 3/5 that you're in the same group. If I ask you, can you relabel those 4 vertices with the maximum likelihood they may have, to maximize their likelihood? What would you do? Well, there's lots of 2s here that makes this guy to be a 2, to make all these edges happy. Here you have 1s that makes these 2 guys be a 1. Now this has 2 1s and a single 2. You want to make these edges happy, you make it a 1. Okay? If you do Bayes instead, you want to marginalize over these middle guys if you just want to recover the root. So what you would do here is that now you have to take into account the 2 possible values that V1 can take, not just the most likely. So here 2 has a very high confidence to be in community 2. All right. 1 has a pretty low confidence. It could be that just some luck made these 2 guys being 1. So this will be more likely to be 1 and these 2, but now if you look at the confidence and you aggregate those 3 beliefs, then this will actually now, with the value that I chose and the number of nodes, this will say, okay, I should be in group 2, not in group 1. So the cut you would, if you look at where you put V0, before you have the thinner cut, as we expect for maximum likelihood, now you have a thicker cut, but this is maybe much more sensible because this guy is very sure to be in group 3. So that's the outcome between ML and Bayes. This is what ML doesn't quite capture and why it can produce things that are sometimes of this nature. So now this was a toy model. How do we actually compute this true marginal? The probability of a single vertex being 1 or 2, just a dummy, given the entire graph. So imagine that you just look at the direct neighbor, and let's make a simplifying assumption, which is that these neighbors, if you forget about the nodes that you try to compute the marginal from, so remove it from the graph, let's assume that these neighbors are roughly independent. Why could we assume that? Well, if you are in the SBM or tree-like models, the loops are pretty down there with high probability, logarithmic depths. So those guys are roughly, in fact, independent. So I call Qi this marginal of each of these nodes here, given that you ignore that one. So now it would be easy to compute if you had those marginals. We have no idea how to get them, but if you had them, it's easy how to aggregate them to get this node. It's again just Bayes rule. So this Q channel is again the channel you get from the probability that you have of being the same group or not when you have an edge. And that's just Bayes rule. K is 2 here, and that's computing this guy from the beliefs of these direct neighbors. So that's exactly how you start when you do belief propagation. Belief propagation is iterating that by saying, okay, now I want to get these nodes marginals, so I'm going to go to their neighbors, and I'm going to assume that these guys are roughly independent. Of course, when you tell to V prime tell to V is marginal, it's going to use now the marginal and V double prime tells to V prime, but V double prime has to ignore both V prime and V. And so by the Markov property in this case is simply V double prime should not, you should look at the neighbors here, but you shouldn't look at the same guy again when you iterate this. In other words, when Sasha tells me, when I have to tell Sasha who I think he is, I should not take into account your last message, otherwise we go into this echo chamber. So that's exact on the tree. If you do this iteration to compute the marginal, on the tree it's exact. If you're tree-like, you hope it's not too far. And amazingly, on the SBM, this is giving you, we believe it's a conjecture with the right marginals, which is pretty amazing when you start with a random guess at the beginning.
Why?
Sorry?
Why do you think that?
Why? Because the SBM has this tree-like, locally tree-like, so this approximation seems to actually be not too hurting you, is actually giving you the right thing.
Do we have results to say if your graph is locally tree-like, then belief propagation isn't insane?
Yeah, there are results of this kind, yeah. Okay, there's often variance. Like in the SBM, for example, we don't really do it with, we don't yet have it with a random initialization. What we have is, what I'm going to tell you next, is the linearized version of BP that we can prove, but it doesn't give you the right marginal. But we can prove it gets you at least weak recovery. Now, some major issue about BP is that A, those updates rules are nonlinear and kind of sometimes a little bit tricky to estimate. In the SBM, it's not too bad. But they are very dependent on the model. To compute correctly Bayes, it's very important that you know your parameters. And when you go on a model where on real data, you have to learn some values for these parameters. It also doesn't generalize necessarily to models like the GBM that I mentioned. It does because you have tons of loops, so all the approximation breakdown, and even to write down the update rule is complex in those models because there are hidden variables, the geometric locations. So this is something that was proposed in the context of the block model. Why don't we simply linearize belief propagation, meaning approximate those ugly formulas close to the uniform guess that you do at the beginning. So I skip the details here because I want to get to the graph powering. If you work out the linearization of BP, what happens is that those recursions now give you a power iteration on a linear operator. You can write down what this linear operator is. And because you don't want to use, when you tell that beliefs, you of course don't want to use that node from here to here. This is the matrix that comes out of it. So it's the non-backtracking matrix of a graph. It acts on the number of directed edges. So you look at your graph and you make it directed. Put 2 edges per edge, one in that sense and in the reverse direction. And you put a 1 between entry E and F of the matrix if F follows E, so if you have this continued extension. But you put a 0 if the edge loop back or if the edges are disjoint. So that's exactly capturing what I mentioned before in the example with Sasha. We don't want to loop back in our belief. So taking a power iteration on this operator, which corresponds to the second eigenvector, is roughly linearizing the previous algorithm. So this approach was proposed. So the good news is that it actually solves weak recovery in the most challenging regime. So in 2 group, it has a nice expression. In K group also, I'll skip the details. This is optimal for 2 groups. We can prove only for 2 groups because starting from 4 groups, we have these computational gaps that take place. So the ideas and heuristics behind the non-backtracking were first proposed in that paper. That's where they give the name of spectral redemption because spectral used to fail. Now you have a new operator that actually works. So that would be the answer to your question. See, that's not quite a Laplacian. And this was first proven in Bordenave-Massoulier-Lalarge for a family of SBMs. Then we did it for the general case of SBM here. This is really using the spectral methods, analysis of this operator. Here we study the power iteration, the BP-like approach. And these are 2 papers that obtained that thing with slightly different methods earlier. There's a survey that I wrote that gives a much more detailed references about these works. I'm skipping a lot. That's the rife intuition of why this non-backtracking operator works in the block model. Remember we said before, if you take a high degree node, you create energy by just, when you power, by just going too much around these nodes. When you use the non-backtracking operator, because you cannot go back, you force the operator to push you away. Then when you take powers of this non-backtracking operator, you leave this high degree node. And if you leave the high degree node, because in the block model, you don't end up in another high degree node with high probability, that makes that you no longer get disrupted by these high degree nodes. And now you focus on the communities. That's the rough intuition. Okay, so how much of a redemption is it really? So here is the geometric block model. You use the non-backtracking spectral algorithm. And this is the cluster that you obtain. What you pick is a tangle, which is a collection, that's a very dense region, which is denser than the other ones. A bunch of cliques that are all intertwined.
This is in 2 dimensions?
This is 2 dimension, yeah. And the explanation is very simple. Well, non-backtracking makes you move away from a high-degree node, but in a graph like this with tons of loops, if you have a high-degree node, you'll go back to it.
Is this expected to happen when the dimension grows?
This dimension, it will help you when it grows, yeah. But it will happen for any lower dimension. If you have a large enough dimension, probably it will be better. All right, so as spectral, we can probably prove this. As spectral SBM fails due to tangles, at least in some regimes. What works in the SBM is the good old normalized Laplacian. Because in that case, I mean, it doesn't always work. We still have cases where it catches a tail, but in that case, the random walk seems to stabilize much more in the two groups here and doesn't cross as much. And it actually, see, that's a perfect reconstruction of the nodes. You do what would be optimal, the two groups, and split them in the middle. But remember that the normalized Laplacian fails on the SBM because now it catches those tails. So you can see where I'm going. The question is, how do we curb the enthusiasm around the tangles? Like BP, those kind of methods, they go too enthusiastic around the tangles without promoting tails. If we smash down those tangles by their degrees, now we may let these other guys that are outliers become too important. All right, so this is the proposal that we have, graph powering. So what's graph powering? So if this is your graph G, give you an example of powering, you simply add an edge between two vertices that are close enough in the graph distance. So a power of 2, I just add an edge between two vertices of a distance 2 in the graph. And you keep the older edges. Power 3, I add an edge between everybody at distance 3. So now these two, for example, get connected. If I do another power, I get a complete graph in this case. So the definition, graph powering for a graph G, the rth power of the graph corresponds to adding an edge between any vertices at distance at most r, less or equal to r in the graph. It has a nice and simple way to represent it in terms of the adjacency matrix. So take A, and I'm adding self-loops to the graph. So I'm putting 1 on the diagonal instead of zeros. So identity plus A if you used to work with the 0 diagonal. Now the power, a graph has an adjacency matrix of A parentheses R, which is simply, well, if you just do power of this original adjacency matrix, you are counting walks of length R and less between I and J. And this would be a very uninteresting operator because you just, the eigenvalues of this guy and the eigenvectors are, well, the eigenvalues are scaled by R. It's lambda I to the power R, and the eigenvectors are exactly the same. So you wouldn't do anything by doing just this. So graph powering is simply thresholding that. You take your R power, and then you just look, if this is more than 1, I put a 1, otherwise I put a 0. So you're back to a graph. You start with a graph, you get a new graph, but you add evidence, you sort of complete the graph where maybe there should have been, there's enough evidence that there should have been an edge. So rough intuition of why this is doing something that, how we actually got to that. Remember that in this example, the min cut was here, but this is not what we wanted. We wanted to take confidence. So if you had these extra edges that were here, now you can see that the min cut is no longer here, it's here. So you make, in fact, this guy in the group, you put your min cut here, you make this guy in group 2. So in a sense, adding those edges is going to make some cuts that may be direct cuts that may be thin, but they're not the right one. If you look at this further evidence at the further distance vertices, now notions of cuts might be again on the right side. But we have to be careful. We want to do this kind of thing so that we don't count too much the loops. So if I were to just use the power of the matrix, which we know is not a good idea, but then this would tell me that these two vertices have, if I do 3 powers, they have 2 paths of length 3 here, 2 walks. So that would tell me there's twice more confidence in a sense that they are in the same group now because I use these 2 paths, which we know is not the right approach if you do base optimal because they share an edge. So graph powering is doing something, it's not clear why it's the right thing to do, it's just thresholding that. It's saying, okay, I use evidence which is deeper, but I don't want to get too much overwhelmed by this evidence in a sense. I don't want to just add it additively. It's not clear. This could look like we undershoot now maybe, but actually you don't undershoot, you still overshoot. That's a surprising thing. And this is how it handles tails. Imagine you have a dense graph, say take a click for example, and you had this single vertex out. If you take the cut of this edge is very thin. But if you take only one power on this graph, then you absorb that edge, right? Because now it's adjacent to everybody in this graph, so you completely remove it. So that's a bit vague. It's just intuition, but basically powering does a decent job at getting this deeper feedback without amplifying lips too much, and while it absorbs the tails. So before I'll give you a few numerical results. So that's the SBM with these parameters. That's close to the KS threshold. By the way, I keep saying KS threshold. That's this threshold for when recovery can be solved. It's just the name KS. So the different, we tried the adjacency matrix, Laplacian, normalized Laplacian, non-backtracking walks, and this powered adjacency matrix. So we do spectral method, but on the second eigenvector we pick, but on the powered graph. So as you can see, as expected, the purple is the non-backtracking walks is doing very well. And it succeeds all the way down. That's essentially close to the threshold. This is the dimension and the number of vertices growing. Now, if you look at this method, the adjacency matrix and the Laplacian, they do well at the beginning. And this is because the high degree nodes don't kick in. This log n by log n is too small, and the good eigenvalues are still the one that you like, so they do pretty well. When you go to dimensions that are pretty large, 10 to the 3, 10 to the 4, then they crash down eventually. But when you power the graph, then you stay and you follow the non-backtracking walk. Now that's on the geometric block model. Here you can see that the normalized Laplacian does pretty well. The random walk catches the cluster pretty well. As expected, non-backtracking walks does poorly, and all these ones, non-backtracking, Laplacian, and also the adjacency, they get this type of outliers that I described before. And powering does fairly well. This is powering. Here it's between 2 and 7. Here it's between 2 and 25. So you can see that I will have to discuss a bit, wait a minute, how many powers can you take? We'll have to talk about it. And that's now in the hybrid block model. Now I have both lots of tangles, but also low diameter. That's the mixture model. I took the same models as in the previous slide, but mixed them with probably half. As you can see, power Laplacian, the power graph does pretty well, spectral. The second one that does fairly well is normalized Laplacian. The other one, they don't do well. Okay, so now the spectral resurrection, it's after the redemption. So there exists R, and you would take R to be epsilon, for example, times the diameter. That works. It has to be large enough. It could be smaller. But if you want a generic result that works for all the models, you would take some arbitrary small, there is some small epsilon positive for which if you multiply the diameter and you power that much, then you saw weak curving on both models, SBM and GBM. And also, we believe that you get exact the optimal fraction of nodes on the GBM. To get the optimal fraction of node on the SBM, you need to use the model parameters. So these spectral methods will not get there. You have to run BP eventually. So now that's the picture that you have to kind of remember from this talk, if there's anyone you should remember. So this is, remember, that's the ugly spectrum in the constant degree regime of your, that's for just the SBM. The guy that you look for is hiding in those high degree nodes and tangles. If I do a to the power, just algebraic power, we know that everything is going to scale to the power r, but this guy stays in the middle. Nothing new happens. If you take the graph powering, what happens is those two guys scale faster. So everything scales, but the informative eigenvalues, they scale faster and they will stick out again. So for the SBM, the first paper of Masouli that proves how to get to KS threshold uses something which is not too far. It's counting passes of a given length between two vertices. So that, I think it's important to discuss the differences. So it's called A square parentheses R between I and J. This would be the number of R self-folding walk, so path, between I and J. And R is taken logarithmic in the paper. Whereas here, what we do is we first have this this powering. Well, if I want to make it look a bit closer to this operator, you can count the number of less than R paths between I and J. But then I just put the indicator function. If you count the number of paths of length R or less, it's the same as counting walks. So already this is helping with the complexity. Because counting paths, if you're not in the block model, if in the block model, passes and non-backtracking walks are about the same, so you can do this efficiently. But in another model, counting paths is going to be expensive. Whereas because you don't look at exactly R, but less than R, you can just count walks. So that's a first difference, but the most important difference is this indicator, which is very important. Because if you use that on the geometric block model, you again have the problem of tangles. You overshoot with the tangles. So this thresholding is the key new ingredient. And this is also helping with the complexity on graphs that are not the SBM. The other thing which is nice is if you care more about the mathematics of it, this goes from a graph to a graph, because there's lots of nice things that also happen. I'll mention a few in the next slide. And so what's happened now is that if you look at a sparse cut in the power graph, this corresponds to a sparse deep cut in the original graph. So you know that if you look at in the original graph at the sparse cut, you get a bad cut. After this powering, basically, the cuts that you look now, they're not just cuts because they look at these walks, and you count how many of them. But so let's see. We said, do we get a few more minutes after? No.
After 30?
No. Then when we started when?
Started like 34.
Yeah. I mean, I don't really need to overgo. It's just you want to see a graph with the difference between a cut and a deep cut or not. An example.
You already gave one, but...
yeah, okay. Yeah, I mean, we can stop here, but the tree was a bit incompletely done. I didn't put all the edges. So it's very simple. You do something like that. Okay, so now the min cut here, the min bisection is going to be here. You have a score of 2. If you power the graph, you add all these edges, and here you have to add a lot of edges. You see, now this guy gets connected to this guy, and this guy, and this guy gets connected to this guy, this guy, this guy. So now you can see that if you count, the new cut becomes here. That's just an example. Anyway, that's a bit high level, but basically now this is going to catch the communities as opposed to...
This is a theorem? Like this picture?
This one, yes. This gets SDP.
No, not necessarily. If you power the graph, then the eigenvalues move that in that way.
Oh, that's the result that I'm presenting, yeah. Yeah, so I mean, we don't know yet what the paper is going to look like. It's already very long, and we want to keep it short. We don't know what we're going to fully prove or not. It's still in there. But that we know is true, yeah. Right, so now that's a more precise picture of what I said before, if you want to know. So what really happens is this. If you take a power which is that large, this is the top, this is the Perron-Frobenius that correlates with the all-one vector. That's the guy that we care about. They're off by a constant. Then I call the name Ramanujan-like is because if you work with a deregular graph, a random deregular graph, you know that you're almost Ramanujan, which means that your spectrum is, there's the D eigenvalue here, and then there's the 2D minus 1 here. Now you know that if you take an Erdős-Renyi graph, then we don't have at all this type of separation, so there's not no value here. But if you actually if you just care about getting the general behavior of getting Perron-Frobenius and square root of Perron-Frobenius, then you get something which is similar, except that there's two regimes here. In the first, this is the high degree nodes now. They are like the degree to the power r by 2. plus something that is only small compared to this dominant term. And then you have here the bulk, which are the, if you take a random vector and you apply it to the power graph, then it will catch the r by 2 plus constants. So if you really only forget about all the O's, even those bigger O's here, because this is small compared to r, then you are basically Ramanujan-like for the power graph. Well, I'll skip the derivation of that. Okay, so here is something that matters also for application. Powering to the constant time the diameter can be expensive. If your graph has 500,000 nodes and you have to power 50 times, you can see that it's not impossible. We've done it with graph of dimension 300,000 on a laptop. You can do like up to 20, 30 powering. But the combination then is as follows. If you really want to take R to be practical, what you can do is combine powering with normalized by degrees. So you power first a few times so that you don't make your normalization be too sensitive to now sparse region. And then you normalize by degrees. So now if you do this powered Laplacian, now you can take, instead of a constant times the diameter, you can take it to polylog and still get the thresholds. I'm putting something under the rug is that we also do some regularization before. So there's a few things I'm a bit hiding. But this is essentially log to the power 3, which is much better than. Now here is something that I'm very interested in is can we combine powering and sparsifying? So sparsifying is you have a graph, it's maybe dense, and you can remove some edges, put zeros, and you change the weight of other edges in a way that you preserve the quadratic form of the Laplacian. Powering is some sort of dual operators in the other sense. You start with a graph that could be sparse, but you add edges where there's some evidence that there should be edges, and then you regularize the spectrum. So now can we combine those two in a way that we add all these edges and then we remove them all? Can we power and sparsify on the fly? That would be good because it will allow us to not go into this issue of having to power everything. And it will also be interesting to see what happens. So if you take a graph, an Erdős-Rényi, we know it is far from having a spectral gap. Let's say we power it. So now we make it have a nice spectral gap, which is almost roughly optimal. Then what happens if we sparsify that power graph? Do we get an expander? Do we get something which is sparse and has a spectral gap? So that could be maybe a new way to construct a graph with good spectral gaps. Real values, I guess, real data set I'll drop. So some more things we're working on. That's what I said before, powering to extract spectral gaps. Powering in Chigger, it seems like in many instances, we even thought maybe in nearly all, but we have counterexamples. If you power a graph, you seem to get to tighten Chigger to the lower bound. So the conductance becomes tight to the eigenvalue, not the square root of the eigenvalue. That's what I mentioned before. Okay, and okay, we have a version for weighted graphs, but okay, I think that was enough. Thank you.
Any questions? Yes.
Yeah, so if I understand correctly, basically you're saying that graph powering fixes the issues that we're having with the spectral methods. Does it also help with the issues with the min-bisection problem?
With the what, sorry?
With the min-bisection, if you just solve that directly.
Oh, okay, so you can do min-bisection directly. So then you have this problem that I just erased, that in some cases on the SBM, you may still cut the periphery. And
right, but does graph powering also
yes,
help?
yeah, it would, yeah. Yes? Sorry.
Just to make your paper longer, did you consider other possible functions of the number of walks other than the identity or the threshold?
Yeah, very good, yes. So we have a discussion about that. So here is something that instead of taking the identity, we thought, okay, what if we take some nonlinear kernel here? Sorry. And for long, I kept telling Colin, I think like this is maybe too strong to flatten it at 1. Maybe we should have a small. So now Colin convinced me that this is the other way around. We should actually make this go down even more than the indicator function. So if you don't want to use the powered Laplacian, if you don't normalize by degrees, most likely the optimal function is a thresholding that goes down. Because you still tend to overshoot, but once you have all these loops, all these tangles, if you don't normalize by degrees, you just power is not enough. So now there is probably a business of understanding the perfect kernel depending on different models. And you can probably derive the right kernel if you want to maximize the accuracy of your algorithm. But the risk is that, again, this is going to be a discussion that is very much model dependent. And for the GBM or for whatever, you will do something different. And we were kind of trying to go away from having worked a lot on the SBM to overfit. So we said, this just sounds like something simple, and that is doing fairly well on quite a few things we tried, even real data.
John?
I was just going to ask about the weighted graphs. I mean,
oh yeah.
So you just put an exponential in front and shrink down the weight.
So that's the natural thing to combine the weights. So if this was a normal graph, it's just is there a pass or not? Then you have to be careful, because let's say that you normalize your weights to be all between 0 and 1s, then long pass will count nothing, so you have to rescale by the length of the pass. And then this is one possibility. It takes the most likely, the highest signal you get between 2 points. So that's like the thresholding effect. So that's a bit heuristic. We don't have result about that. And one thing that I'm hoping...
Imagine here, non-linearities might come in a lot more strongly.
Right, yeah.
I mean, who knows,
Yeah.
right?
But we are hoping, so Henrik, if he has time in his senior thesis, will try to apply this to the Wars embeddings. Instead of doing log PMI type of things, that's kind of the extent. That's what we think is the natural extension of that, and we'll see how it does. So if you don't hear from me, it means it didn't go well.
Well, you can tell us if it didn't work as
Yeah,
well.
no, of course, yeah, I'll tell you. Yeah.
So in the interest of time, maybe we should take the rest of the questions offline, and so let's thank Emmanuel. And we'll come back at 11.
Merci.